Have you ever wondered how to choose your route when climbing a mountain? Consider the mountain in the picture and you want to choose the direction you have to go. But to do this, first you need to know the slope in any direction, because you want to avoid steep slopes. Recall that if the mountain is the surface given by the function z is equal to f of x and y, then you can use the partial derivatives of this function to find the slope of the mountain in the x and the y directions. You can find the partial derivative with respect to x in a point x0, y0 by drawing a vertical plane parallel to the x-axis and through the point x0, y0. If you then look at the intersection curve between this plane and the surface z is equal to f of x and y, you can use a tangent line to calculate the partial derivative with respect to x. This finally gives you the definition of the partial derivatives. For the partial derivative with respect to x, you do a small step of length h in the x direction and calculate the rate of change. Finally, you take the limit of h going to 0 and hopefully arrive at a value. If you want the slope of a function in the x direction, you basically want the slope in the direction 1, 0. Similar, the y direction is given by 0, 1. What would happen if you instead look at another direction? Consider the slope at the point x0, y0 of a function f of x and y in a different direction. Say u is ab, with u a unit vector, and give this slope the name duf, the directional derivative of f at x0, y0 in the direction of u. Similar to the normal partial derivatives, you can draw a vertical plane parallel to u and through the point x0, y0. Again, you get a curve, the intersection of this plane and the surface z is equal to f of x and y. If you travel a small distance h from x0, y0 in the direction of u, you arrive at the point x0 plus ah, y0 plus bh, because u is a unit vector. The function value then changes with delta f equal to f x0 plus ah, y0 plus bh minus f x0, y0. If you then divide this change in the function by the distance you traveled, you can approximate the slope duf by f x0 plus ah, y0 plus bh minus f x0, y0 over h. If you take h a little bit smaller, then you can expect that the approximation becomes a little better. You can even take h again a little bit smaller, and smaller, and smaller. Of course, h0 does not make sense, because you are not allowed to divide by 0. You are, however, allowed to take the limit as h approaches 0, similar to the definition of the partial derivatives. You have now obtained the formula for the directional derivative of a function z is equal to f of x and y at a point x0, y0 in the direction of a unit vector u equal to ab. We can formulate the precise definition of this directional derivative as the directional derivative duf of f at x0, y0 in the direction of a unit vector u equal to ab is duf equals the limit of f x0 plus ah, y0 plus bh minus f x0, y0 over h as h approaches 0, if this limit exists. Let's calculate the directional derivative at 1, 1 of f of x and y is equal to f minus x squared minus 2y squared in the direction u given by 3 over square root 10, 1 over square root 10. Notice that u is a unit vector. First, you calculate the function value in 1, 1. This gives f in 1, 1 is equal to 1. Second, you calculate the function value at 1 plus ah, 1 plus bh. After simplification, you get f in 1 plus ah, 1 plus bh equals 1 minus the square root of 10h minus 11 over 10 h squared. Now you can take the limit for h going to 0 of the difference between result 1 and result 2 divided by h. First, you simplify as much as possible. Now you know what the limit value is. You can just plug in h now, so the limit is minus square root of 10. Using limits may not be the easiest way to obtain a directional derivative, but it gets the job done. In class, you will learn an easier way to obtain a directional derivative, and you will be able to calculate the direction with the steepest slope. See you in class.